I do hope I am loud and clear. Yes. Hello. Yeah, very good. So, I do hope everyone is doing well now that the weather is changing and everything. Yes. So, this week happens to be the last week for Fractal 2 before we have Minor 2 next week. Hmm. So, I am very sorry I won't be able to take the class tomorrow, which is the last class for Fractal 2, but we have the convocation tomorrow and I have certain duties over there. So today I shall try to give you an overview of the last two topics that are there in the syllabus, which covers hidden Markov models and Kalman filters. I shall try to give you an overview. Now, and tomorrow, our TAs, which is like Tejas and Arpit, they will try to give you demos of these two topics. Okay. And I really am sorry I won't be able to see you tomorrow. So what we'll do is I'll try to give you an overview over here. Tomorrow we'll have demos over there. And if there are any questions or any doubts or anything that you would like to discuss, please feel free to drop me an email. Okay. Please feel free to do that. Don't worry about times and I shall try my best to get back to you at the earliest I can. Okay. I shall try my best. And to be very honest, the topics that we are doing today is not something that everyone understands very clearly, because what we are essentially trying to do over here is trying to model the real world that we don't understand, and we are trying to use some kind of a mathematical model in order to understand the real world. But to my understanding, uh, we don't understand all the parameters that go into describing the real world. So whatever we do, no matter how many parameters we try to plug in into our equations and models, there is always something that we perhaps don't know. Right? So eventually you will always have to modify your model, update your model, adapt your model to kind of meet the better understanding of the world, right? So these are two strategies, the hidden Markov model and Kalman filters, that that help us model or kind of arrive at a prediction over time of a dynamic real world situation. Hidden Markov models are something that we use to model a rather discrete state phenomena, while Kalman filters are something that we try to use or we use in order to model a more continuous situation. Right? So the perspectives of these two are rather different. I shall try to allude to them over as the class progresses. And to be very honest, I will be actually trying to uh, explain a topic that I too am rather curious about and rather unsure about myself. So maybe I will have to have a hidden Markov model to predict my uncertainty as well regarding the topic. Anyway, so what I have done is I haven't actually prepared slides for this because there's a lot of mathematics involved. I've written a few pages in very bad handwriting on my graphic tablet, and I shall try to explain using the same. Okay, so hopefully it will be everyone will be able to see what is happening. Okay, and for here, I'll share my screen. Yeah, so I suppose everyone can see it. So the resources slide, yes, the resources slide that I had. Did I share the resources slide with everyone for probabilistic reasoning? I didn't do it. Oh, I'm so sorry. I'll do it at the end of this class. I'll be sharing it up. I'm so sorry. I forgot. So I'll put this up. And over here, we have a list of certain video lectures that have always helped me understand these topics. And the ones that are in bold are the ones that are particularly excellent to help you understand the topic. Okay. I have primarily followed the textbook by Norvig, and it's these two lectures, as well as the one from IIT Kharagpur. That one too is very good. I'll make it bold. Right. But the one from Berkeley is particularly outstanding. And it is essentially, it derives from Norvik's book. And the one at the end, the last one, this one is for Kalman filters. It's actually a series of 55 lectures on Kalman filters, each one about 10 minutes or so long. But it's a beautiful series of lectures. And if you listen perhaps to the first 5 or 6, you will get a good idea of what Kalman filters are. Okay, the first 5 or 6. Well, this is a series of around 55, 58 lectures, the first set. So that's that. And before I move on to the class, I'd like to let you know that in the previous class, I had received requests on if I could share some code and examples for reinforcement learning. Please look at the resources slide for reinforcement learning. I have added 2 links to repositories, excellent repositories for problems, solutions, and code. Okay, that will be on the reinforcement learning resources slide. Right? I have added that. So I'll be referring to the slides that I shared the earlier day, in the earlier class on the introduction to probabilistic reasoning over time. Everyone can be on this set of slides for easy reference. Yeah. So over here, what we were essentially trying to do is observe a certain sequence of evidences or collect a certain number of evidences and then arrive at an understanding of what the state of the system is. Okay, this is what we were trying to do, draw inferences on states of the real world or a situation that I'm trying to model. If I show this diagram, if these are certain states, I don't have access to these states maybe, but what I'm trying to do is look at certain observations, look at the probabilities of their occurrences, and then try to arrive at an understanding or some kind of a representation of the states that might be causing these observations. Okay, there are many examples. There's a classical example that almost all lecture videos seem to have or seem to allude to is it's a sunny day or it's a cloudy day is evident through a person's expressions. If the person is happy, it apparently means that it is a sunny day, and if it's a sad expression, it apparently means it is a sad day. It's a cloudy day, and so I don't see the states of the environment or the climate or whatever. But what I do is I look at the person's expressions and try to figure out what the weather of that place might be. Okay, so this is essentially what we are trying to do over here in probabilistic reasoning over time. Here, what we are doing is we are dealing with Bayesian networks that grow with time. See, this is if I'm over here at time t, there is a t minus 1 sequence of observations and inferred observations, and and a state that led to that observation, and so on and so forth. Right. So now the basic steps of inference in temporal models, if I refer to the slides again, are filtering, prediction, smoothing, likely explanation, and learning. Learning, which is a mix of filtering, prediction, smoothing, and a back and forth traversal of these. So, in filtering, what we are trying to do, I'll just recapitulate this a bit before I move on to hidden Markov models. So in filtering, what we are trying to do is I have a set of evidences or observations across time, say point 1 to point t, and I try to derive at the state that xt is, that my system is in. In predictions, what I do is I have a set of states up till time t, and I try to look ahead, a certain number of steps ahead. I could look at just one step ahead or n number of steps ahead. Right? In smoothing, what we do is I have a set of observations. I had made a prediction once upon a time, means I had made a filtered or perhaps a prediction at some point in time k, which is less than t. And now what I do is, based on these new evidences that I have received, I try to revisit my solutions and correct them and update them. Okay, so what I do is at point t, I make a prediction for, say, point k, a few steps ahead, which is k. For example, I have this kind of an equation, but then when I reach point k in reality, I go back to my prediction and I update it. Okay, this is what smoothing is doing. And likely explanations are, I have a sequence of words or say sequence of states, and I try to find out which is the most likely sequence of states given just the observations that I have. So we have this argmax kind of an equation. So these are a few things that temporal models that we try to work around with temporal models. And now I'll share this awfully handwritten set of pages that I have made. So now in hidden Markov model, in hidden Markov models, what we have is we just have these observations and we have no way of seeing these states. It's only through these observations that we can infer the states. Okay, and as I just mentioned a couple of minutes ago, that we are working in discrete time. Okay, so what I'm trying to do is for my, I have a set of transition probabilities. If I go back to this model over here, I have a set of transition probabilities which tell me how I move from one state to another. This is something that I infer from my observation, and I have a sensor model over here. Okay, which allows, sorry, I made a mistake over there, sorry. Transition models are predictions of moving from one state to another state here. One state to another state, if I just depend on the prior state or the step just ahead at xt, if I'm just focusing on xt minus 1, I have the first order Markov modeling happening. If I look at 2 steps back, then I have an order 2 and I can go on. I can go on to n orders. And for sensor models, what we have is I look at observations and I try to arrive at certain conclusions on the states. Right. So this is exactly what we have for hidden Markov models. We have transition probabilities, state transitions, and we have sensor probabilities, which is this set of equations, observations. And we have a start state from where we look at the entire system that I'm trying to model. And the initial distribution is something that I just randomly start with. In most cases, you will see that it's, for example, if you have 2 states, you will have 0.5 probabilities given to each state. But if we are working on a hidden Markov model, we will just have maybe one state and we will give it some kind of a random probability. Okay, say 0.6 or 0.4 or something like that. It will be random, and our goal is to converge after a certain number of iterations of forward and backward, like filtering, prediction, and smoothing. The aim is to iterate across these number of steps to converge to a certain set of inferences that no longer change. So in a way, I say that once I reach that particular time t, somewhere near infinity, and my solutions no longer change, I perhaps have arrived at a model or a good model of the situation that I'm trying to look at. Okay. So now what we have is we have these states, state 1 and state 2. From each state, you have a certain probability of observations coming in. Like for example, if state 1 be it is a good day, it's a sunny day, and state 2, say for example, if I want to write, this is a sunny day, and this is a cloudy day. So if I am, and see my emissions, E1 is I am happy, and here it is I am sad. Similarly over here, you can use any example. This is just a classical example that's there in all the books. So I'm just trying to use the same. So I have a transition probability that if it is sunny today, I could, the next day, it could be sunny again. So that is why my probability of state 1 to state 1 over time is A11. And it could be sunny today, it could be rainy tomorrow, so I have A12 and so on. So this is essentially a connected graph. Okay, this is one way of representation. And I have certain probabilities of state and observation consequences, meaning if I'm in state 1, it's a sunny day, and I am observed to be happy. So the probability of that happening is B11. And then it's over here, it's a happy day, but I happen to be sad. So there's a probability of B12 of that happening, and similarly over here. Okay. But now what I would like to call your attention to over here is we are not essentially embedding semantics of the entire environment over here. Okay, we have no reasoning at this point in time. What we have is a set of transition probabilities. We have a set of observations. When I need to, observations in certain books, you will find they use emissions because these are like emitted from a certain state. But we have actually no understanding of why is it so, like why is it happy? Why am I always happy if it's a sunny day? We don't embed any of those semantics, or nor are we trying to even understand that at this point in time. Okay, so now the question that we come over here is, say you see a certain person on the 5th day, and you have a record of observations over the last 4 days, and you see that person is happy. So you try to kind of understand what the weather must have been, or what the weather is today and what it was yesterday. Right? So you have a set of observations over 4 days, and you know that this is how it works for the person. So then on the 5th day, when you see the person, you try to understand what the weather is like, and what it must have been the previous day. Okay, so it's like you're trying to find a sequence of observation, a sequence of states that might have led to the 5th day observation happening. So that's what I've written over here. We see evidences over a certain time span and try to arrive at some conclusion of the system state. So now these are representations. We can either do it through a graph, or we can write it on a table over here. Time t time t plus 1. This is for time t plus 1. These are my states. These are probabilities. These are probabilities of states, state transitions, and these are emission probabilities. So now the question that I have over here is, I have a set of observations, 1 to some t plus 1, and I want to find out the state, right? Just the example that I gave. I have this 5 days of worth of observations, and I want to find out what for 5 days I've been seeing the person happy, sad, and now I want to find out what the weather is like on the 5th day. So now I can expand this. So now can someone tell me what this expression is of? What operation are we talking about over here? Are we talking about prediction? Are we talking about smoothing, or are we talking about filtering? Can someone tell me what operation are we trying to do over here? This operation over here, what are we trying to do? Isn't that? Is it prediction? Because did you see the observations over here? If you look at the observations, I have t plus 1 worth of observations. If I show you the slide, see over here, if you look at this, right? Yes, yes. That's exactly what we are trying to do over here. This is a smoothing operation that we are trying to do at t plus 1 at the time. Okay, this is, if it had just been t plus 1 here and a t over here, that is when I would be doing prediction. Okay, so now I can write this as this, because it is, I have the set of observations, a set of observations, inferences, and a new observation at time t plus 1. So now I can expand this to this using Bayesian rules. Okay, x t plus 1, a comma b, if this is a and this is b, then probability, this joint probability, I can represent it as conditional probabilities in this sequence, likelihood and prior. And then I just rewrite this equation in this form. Okay. So I have b a dot pa. So it's b a and probability of a, which is this again. So if you see, this is where my prediction is happening. This is where the prediction is. And this is something that I get from my sensor table or my sensor table, right? If I show you this over here, this is what I get from this emission probability table. And these are predictions that I have been making over time. Because remember, in hidden Markov models, we don't have access to the state. Okay, I just know that if, say, a person is happy, probably it is a sunny day or something on those lines. If the person is sad, it's probably it's a cloudy day. I just have those information, those set of information, right? So over there too, I am predicting. Isn't it, given a certain observation? Say today it is happy. Today I see the person as happy. And then I try to find out if he's happy today, what is the likelihood that the person, what's the state that he is going to be in tomorrow. So over here, I have been doing prediction across states. And over here, this is something that I get from my sensor table probability. So now over here, if you see, if I go back to this table, there are certain there are set of states, and from x1, sorry, from a given state, I have two emission probabilities, right? All the visible observations are possible from state one with certain probability. One could be zero. That's fine, but we still need to represent it in that way, right? So these set of observations, I need to condition it over a certain state t, because at this point in time, I'm trying to arrive at prediction. Okay. Now, if I already knew what xt is, then I don't have to go ahead. Then I can just plug in the value over here at xt and then move ahead with my calculations. But if I don't know what xt again is, because over here what we're trying to do is reason over time, isn't it? So if I don't have access to what my xt is actually, so then I will have to condition it over a set of states. If you see here, I can have all kinds of possibilities because given these evidences that are there. So I extrapolate this function to all the different states that are possible. I add them up over xt. And so this equation, it expands to this equation over here. And remember, this is where the Markov assumption is happening. Markov assumption, again, I'll show this previous slide over here. Right. Markov assumption meaning that a certain state has all the information required in order to lead you to a new observation, and that we are only focusing on one state at a time. Okay, the current state depends only on a finite number of previous states. And since we are trying to work on first order Markov models, so it's just one state that we are concerned about. Okay. So, right. So this is something that I get from my sensor table. So my aim was to arrive at an understanding of the state given certain observations. I just turn the equation ahead to what the state might have been. If you see that I'm kind of on the borderlines of prediction at this moment, given an observation, and I try to arrive at this or kind of use the information that I have over here, which is a transition probability set of values and plugins that I have made from previous prediction. Okay. I rewrite this equation over here using the Markov assumption over here that this particular evidence I may even overlook because it's just the states that I'm concerned about. And so I'm using these predictions over here, plugins from values to arrive at the future over here. So now what I have is essentially a recursive method of representation of this phenomenon, if you see over here. It's a recursive estimation over here, recursive form of explanation. Here there is a lovely example in the book. I will show it to you. So now this is for smoothing. But if the same equation were not for t plus 1 over here, just a t plus 1 over here, which is the t plus 1th state, then I would be doing a prediction. Okay, and for the smoothing, it would be a k, and we would have certain backward probability, right? Going backward in time. I will show that in the book. So now, this certain set of equations that we have over here, these are all in the book. Okay, I have just expanded a few things over here, given what I have managed to understand of what these different states or what these different elements are trying to explain in this equation. I'll be sharing these as PDFs at the end of the class. So what we have over here is these values that I'm trying to plug in, these are kind of forward messages, right? Because I have observations, I have state understanding, and I try to plug in those values into my state transitions in order to arrive at a new understanding of the state. Okay, a new state or the current state. If my current state be t+1, I'm trying to utilize existing or whatever values I already have or I have evaluated to arrive at some kind of an understanding of what this is all about. This is all about. Sorry. This is all about. Okay. So this is like carrying a forward message. This is what they say over here, a forward message, because I'm using past states in order to arrive at the future through the present. Because here xt, I'm using all the different combinations of xt to arrive at xt+1. xt, for example, say today, whether today is a sunny day or a rainy day, I will just look at the day before me, that is yesterday. Okay, this is over here. So I will do the yesterday. It could have been a sunny day or it could have been a rainy day. So I add up those different probabilities. Right? Is it making sense? xt over here, why I have the summation over here? Because what I have today, I am trying to derive it from what happened yesterday, and what happened yesterday again has two probabilities, right? It could be sunny, it could be happy, or whatever it be. Just one particular state, but two different values for that. So that is why I will sum it up and use the probability of these observations for this given state. So that the reason that we are doing is in order to arrive at this value over here. Because remember, here we don't have access to the state. We are just trying to derive at an understanding of what it could be like. Okay, we are just seeing certain observations, we have certain probabilities, and we are trying to arrive at this new state understanding. Okay, so this is what we are trying to do, is use what knowledge I have from the past, plug in into my present equation. Exactly, that is why you will be seeing that all the reinforcement learning models, we keep on alluding to this partially observed MDP, Markov decision problem, isn't it? Throughout our reinforcement learning reinforcement learning classes, we have been talking about Markov decision models, Markov chains, Markov decision models, partially observed Markov decision models. Right. So now if I have absolutely no idea on what my states are, completely you're functioning in the world with no idea of the states, but just this is Bayes rule. It's not simply arriving by Bayes rule. This is an application of Bayes rule, but just in a recursive fashion. It's just through recursion over here. I'm trying to arrive at t+1 using values of t for previous states. It's exactly Bayesian rule over here, because I've written Bayesian rule over here itself for joint probabilities and conditional probability. This is Bayes rule. And here we have just made this Markov assumption. When I come from this particular equation to this equation, this is where I have a Markov assumption, meaning that my current state just depends on a finite number of states. I'm not particularly concerned about the evidences that I see over here. So I just exclude that from my equation. That's the Markov assumption happening, but the rest of it is all Bayesian. Bayesian sum. Right, so I'll just show you an example from the book. Over here, you see this is this forward thing that I was talking about over here. This forward carry forward of messages into my current understanding of what this new xt+1 should be like. So over here, what they say is I'm trying to arrive at an understanding for something at time t2 using observations across 1 to 2. Okay, 2 days worth of observation. That is what I'm trying to do in order to understand what state at time 2 is like. Okay, just look at the equation over here. I have 1 to 2 and I'm trying to observe what x2 is like. Okay, they just use RT and UT because UT is for umbrellas, for the umbrella situation, umbrella observation. Sorry, where is, uh, okay, over here. I'll write it down. I'm sorry. I'll write it down over here. This is where the Markov assumption is. This, this bringing this equation down to this equation. That I'm only depending on the states over here. Okay, just the previous set of states. And why am I making a summation? Is that clear? Because it's in a way kind of doing a logical OR operation. If I can just find an analogy, doing a logical OR operation in order to find of all the previous days worth of probable states in order to arrive at what my current state is. Okay, because like I mentioned, xt has two values that it can have, say a sunny day or a cloudy day, but I don't have access to the states, right? So I try to use prior probabilities in order to arrive at what xt plus 1 could be. Okay. So now this is a sum that the book has. In fact, this particular sum is used across all video lectures that I have come across. They just use values as sunny day and cloudy day and a happy expression and a grumpy expression. They just use that, but it is essentially this sum that they use across all the books. So I too will follow what everyone has been doing. Okay. Right. Only on the last evidence, absolutely. Only on the last one state. But now if you think about it, that last one state is again derived from its prior state at xt minus 1. Right? So it percolates down to x0. Isn't it? At xt plus 1, I'm using values from xt. Again, xt itself derives from xt minus 1, and so I go backward. Isn't it? This is how the recursion works over here. I'll just show you this example over here. So, yeah. So over here, I'm trying to arrive at the state R2, like whether it is a rainy day or not, given observations of umbrella situations across 2 days. So on day 0, we have no observations. So I just put 0.5 on both situations. Both situations, why? Because it could be a sunny day or it could be a cloudy day. Okay. So that is why I put 0.5 probability for both. So if I draw this thing over here in this diagram, what is essentially happening is I have a start state and I put probabilities for both these two states. I put 0.5 and 0.5. Okay, this is exactly what is happening over here. Over here, in this part. So now I try to find out what R1 is using R0. I have these probabilities given to me in my transition matrix. So I arrive at these set of probabilities. I use this to find R1, U1. R1 and U1, I use that using U0. I plug in these values over here. Now this is a normalization factor that they put over here. That's kind of a learning rate in a way. And then they utilize R1, U1 to arrive at R2, U1. And use that to arrive at U1, U2. This R2, U1 is over here in this equation. over here. So I use values from 0 onwards and I move up to 2. So the second day values. So again, what I have is I start from a start state. I calculate predictions or transitions. Sorry, I calculate the probabilities for new states using observations, which again derive from previous observations, and then I plug those values in to arrive at these values, and then I plug that in into my equations. This is where the summation is happening. This R2 U1 is something that they represent this entire part as. This part. R2 U1. Got it? R2 U1. Yeah, R1 U0 is nothing over there because we don't have any observations. But over here it's a U1. So it's this part of the equation. They put the summation over here to find the value, and then they plug that value in to arrive at this. If you read the book, you'll be finding that these values are all given in a transition table, and these are just products happening, one-to-one products, 0.7 into 0.8.1 to give you this value. And they have used a normalization factor over here. Okay. Is this making sense? You just have to see the book in order to plug in the values over here, but this is just a recursive estimation. We're using R0 to arrive at U1, and then we are using U1 to arrive at this new last value. This is on chapter 15 of Norvik's book. Okay, so this is what is happening for smoothing. And for prediction, we use the same kind of equation, but we just leave out a certain thing. Over here, what we were doing is, over here, prediction, I just use observations 1 to t to find out a certain set of look-ahead look-ahead probabilities. Same set of equations, same kind. Okay. But I just don't have this new evidence for predictions. If I'm trying to do a prediction, I will not have this part will not be there. Okay, shall I write it down over here? When I'm doing a prediction, it's essentially trying to find the probability t plus 1 given observations 1 to t. So what is happening? In this equation, this particular value will not be there when I'm trying to do a prediction. I'm just using past experiences to arrive at a new state assumption or new state probability, and just this new value, this new sensor value will not be there. This new evidence will not be there. I'm trying to derive it. Okay. This is what is happening for prediction. Right. Is it making sense? Is it clear? So this is a forward step that is happening, if you think about it. I'm using values that are evaluated before in order to arrive at current or new values. So I'm using a forward step over here. But if you remember, for smoothing, we needed a backward step because I have to go back and correct certain predictions that I had made before. So what we do is same kind of equations, same set of equations, but over here k is just less than t. Okay. See, k is less than t for smoothing. Same set of equations, it's just that this part over here relies on using back values, values that have existed at the past. So I have a um, backward step coming in over here. So I have a mix of forward steps using normalization parameters. You can kind of draw an analogy with a learning parameter happening over here. You learn something in the forward direction, and then you go back. For each step taken forward, you go back and revisit what you have done in order to correct your distribution. Right? The entire process. Sorry, there is a question. First equation, we saw that k equals to t plus 1. Oh, okay, okay. Actually, if you arrive at k less than t, because over here what we are doing is, what we are trying to do is, I have this new evidence at time t. Okay, the reason that we are not using k less than equal to t is, you have a new observation at time t. And that is why you are correcting what you have done at the past. That is why it is k less than t. Because you already have an observation over here, isn't it? You have an observation, you have a state at for xt, and you are using that. It's like you actually experience something and then you use it to correct what you had predicted in the past. So that is why k is less than t. Is that clear? Computing the distribution over past states given evidence up to the present. Now, this is a different operation altogether. Over here, the equation that you have mentioned over here, right? It should to just be very clear. Over here, what we're doing is we're trying to predict something, not predict. We are trying to arrive at an inference of xt plus 1. We're trying to arrive at an inference, but if I am standing at xt plus 1 already, I'm standing at xt plus 1. Right, you can write the equation. If you are trying to take it from the perspective of xt plus 1, then it can be x less than equal to t. But if you are at time t, okay, if you, instead of writing t plus 1, if you are at t, then what do? You are looking backwards, isn't it? So if you are standing at xt plus 1, then you look at t. But if you are standing at t, these are just notational differences, nothing else. Just notational differences. Okay. I am standing at T. I have made a new, when I'm doing when I'm doing filtering, I am standing at T. I have a new observation. I'm trying to find the state, xt plus 1. Okay. Yep, I will. I have new evidences. I'm trying to find out what xt plus 1 is. Right. So this is what I'm doing for smoothing. For prediction, there is no t plus 1. Right. This is smoothing. Here, this is smoothing. Because I have evidences I have made. Right. Because over here, what we are doing is, in smoothing, we are starting from 1 and I have moved on to t plus 1. I have a new evidence already. I already have a new evidence at t plus 1. Okay, I am standing at t. I have a new observation for t plus 1 and I'm trying to find out what xt plus 1 will be like. Okay, but these are just notations. But uh, for sorry, I made a mistake. Over here, this is filtering. Sorry, I'm very sorry. I just got mixed up. Over here, this is filtering. Over here, in this equation that is happening over here in my handwritten notes, this is filtering. Why? Because I am standing at t, at my tth set of states and observations, whatever predictions I on the my entire model that I have so far, I have it all plugged in over here. And I have this new observation that has come in, the t plus 1th observation, and I'm trying to infer what xt plus 1 is. Okay, I'm standing at t. And I have new evidences that has come in. Okay, this is in smoothing. In prediction, I don't have this new evidence. I'm just standing at t and I'm trying to figure out what xt plus 1 is. Okay, and in smoothing is I am standing at t and I'm trying to do what t minus 1 and beyond would have been doing. Right. Yes. I'm so sorry if I made it look confusing, but if you go back to the slides that I had shared over here, the first day set of slides, if you look at what these probabilities are doing over here, and over here. Right. So over there, what I was doing was filtering. So that is why it is less than k. I'm sorry, I think I kept using the wrong words. I'm sorry for the confusion. Okay, so it's essentially the same set of equations that are being used. It's just what values I have and what I don't have. And they're using the same Markov assumptions, the same kind of Bayesian rules to derive these equations. There's nothing more than that that's happening. Okay. So now when we were doing filtering and prediction, we were using forward steps. But since over here, I have this backward step coming in over here, which is the x plus 1th observation over there. That is why I have a backward step, a backward message coming in over here. Okay, so now I have a forward step. It's like I take certain steps forward and then again I move backward to correct my predictions. In fact, this operation over here is quite is clearer in fact if you look at Kalman filters. Okay, so they have examples in the book over here. Here they are taking just one step ahead. Maybe I can now if you think about the situation, if I take for every step that I take, I have to update my predictions or update my distributions for all the previous states, then it is computationally very intensive, isn't it? You just take one step ahead, say at t, I take a new step and I update my predictions or my distributions for all the t minus 1 states. So then it is computationally very intensive. So what I can do over here is I don't update all my steps, but just up to certain recent paths. Maybe say k steps or say p steps or m steps. Okay, I don't do it for my entire table over here. And if you think again over here, does this strategy remind you of a certain programming technique? This strategy over here, this plugging in of values, does it remind you of something? Something that we did in reinforcement learning? Recursion, yes, but what else does it remind you of? Absolutely. This is what I had wanted, dynamic programming. Okay, because over here you are essentially breaking down a problem into sub-problems and you are recurrently using those sub-problem solutions to arrive at a better approximation. Okay, so we can draw an analogy with dynamic programming over here. Very good. Fine. So this is what hidden Markov models are. We are working on discrete states over here. We aren't looking at continuities over here, though it is a continuous real world. but we are not focusing on continuous activities. We're just looking at discrete observations and discrete time states. Okay, so now if I just extend this to a more continuous kind of a phenomenon, that is when I have to use Kalman filter. Okay, now Kalman filters, there are all kinds. There are many kinds of Kalman filters. There is one that assumes that the real world moves in a linear fashion. There is this extended Kalman filter that says that the world is non-linear. So we have different kinds of Kalman filters. Okay, and over there, the essentially it's exactly what is happening, that we have whatever we have described for Markov models, hidden Markov models, which is filtering, prediction, and smoothing. It's essentially the same thing that is happening in for Kalman filters as well, just at a continuous level. I have a set of observations that I'm continuously arriving at, or certain evidences that I keep doing, and I try to conclude what the states may be, but just over continuous time. Right? I will go back to these handwritten notes, but before I forgot to tell you about this. Examples of hidden Markov model. Classical examples, we have speech recognition. Now, if you think speech is a continuous time phenomenon, right? But what I am focusing over here is certain discrete time intonations, maybe certain pitch variations or certain frequency variations of discrete words, not continuous speech that way, just discrete words. So I have certain intonations and I try to find out the words. Words are my states, and what I observe are sound patterns. Okay. Another classical example is POS tagging, which is part of speech tagging. When I do natural language processing, I have words and I try to find out what parts of speech they are. Okay. So then I have affect recognition. This is an example that's not there in the book, but I have placed over here. It is you see certain expressions and you try to figure out whether this person is happy or not. Okay, so it's essentially a continuous data that you are seeing, but what we are doing is you're discretizing it over time. Okay, we are not doing it at a continuous span. We're not having inputs coming in at a continuous pace. It's just that because essentially whenever we are trying to model the real world, no matter how many times you sample, you are actually doing an analog to digital conversion, right? The minute you are trying to model a real world dynamic phenomena on the machines that we have today, you are essentially doing analog to digital conversion. It's just the rate of samples that are changing. If you take it very fast, so at time which near or limits to zero, if that be the pace at which you are collecting samples, you will have perhaps better observations because the time gap between two particular observations will be very less, right? It tends to zero. If that be the case, then you will be saying that my discrete model is very close to the analog real world, right? But the minute you are trying to make an analog real world be modeled on the machine that only understands zeros and ones, then you are doing analog to digital conversion. These computation principles might be very different when we look at quantum computing principles. I suppose that is very different over there. We even have mathematics of Bayesian probabilities for quantum models. If someone is interested, you can look into these things, how it will be changing in the quantum world. I unfortunately don't understand it very well, but maybe someday if we meet and I get the opportunity to study it, maybe we can discuss someday on quantum models and probabilities. But for the time being, this is what we have. Okay, we are trying to, no matter whether we do Kalman filters or we do Markov models, we are doing analog to digital conversion. It's just that the rate of sampling is different. Okay. Are these examples clear of why I use hidden Markov models over here? Are these clear? Because you can use hidden Markov models and also in a localization example that's there in the book. Next step, you're in a grid world and you're just looking at the next step, or you just want to predict the next step. Fine. But in Kalman filters, it's more about continuous movement, like say a bird flying. Okay. I will repeat it again. In speech recognition for hidden Markov models, we are just looking at patterns of speech, intonation, certain parameters at a certain point in time to figure out what these words are. Okay, I just look at these different. When I say a word, when I utter a word, it has a certain intonation pattern, right? So I observe these patterns in order to find out what words these are. For example, if you have these speech to text converters, you say something, it takes in words, it takes in the frequencies of your intonation, the pitch variation, and shows you the words that you have said, that you have uttered, as well as certain very intelligent systems. They try to predict the words that will come up next. When you these days type on Google Mail, you have these predictions coming up, right, of what the next words could be. It's something like that. So discrete state world, new words, you say something, it gets converted into text, or you are writing something and you have the next set of words coming in. For part of speech tagging is you have a sentence, so you have words in front of you and you try to find out the state in terms of the part of speech that this word belongs to. Whether it's a noun or it's a verb, it's an adverb, it's an adjective. But if you have a very good structured language, then it is very easy to find transition probabilities from noun to verb, verb to adverb, adverb to adverb. These transition probabilities are very, very fixed if you have a well structured language, like say Sanskrit is, or maybe German is. But English isn't a very good, a very strongly structured language. It isn't a very strong structured language. So transition probabilities are rather curious over there, are rather, they're not very fixed. That is why we say Sanskrit is a language that I can use to build computational systems, because it is a strongly structured language. My transition probabilities are very fixed from one state to another state. Like the verb will follow the noun, which adverb will follow the verb. These probabilities, the construction of a sentence is very fixed. So POS tagging, or part of speech tagging, is you have words and you try to figure out what parts of speech they are. Okay. For affect recognition is you look at the expression or the machine. You don't look, you think yourself to be a machine. You look at the expression and you try to figure out what emotion this person might be having. Sorry, there was a question. Right. This is essentially what is happening. This is essentially what is happening. I'm responding to Sushil's question that he has sent. This is exactly what is happening over here. It's just discrete words, discrete expressions. It's just that. Fine. And when I do it at a more continuous scale, that's when I use Kalman filters. So now Kalman filters, this diagram over here, this is what it is. I have time and I have observations. These down dots, these are the observations. These are my estimates. Okay, continuous time estimates. This is something that I keep predicting. And my aim is to converge at some point in time, t tending to infinity, at the actual values. If this is my actual line, this is for a linear assumption of the real world. Okay, this is a linear assumption of the real world. I mentioned a couple of minutes ago that we can have Kalman filters to model linear worlds as well as non-linear worlds. This is a strong assumption that they have taken over here. If this is what my actual value should be, I am taking in observations. But over here, why are these? Can someone tell me why these observations are at these points? What is it that is making these observations not actually be on the line itself? Can someone tell me that? Why do you think this isn't happening? Right, measurement error or noise. Okay, there's a certain amount of noise in my observation. There's a certain amount of noise. So now they use a Gaussian noise concept over here, which is the normal distribution of noise, meaning it follows a centrally aligned orientation. The values, they converge towards the center of the probability distribution. So if this be my estimates, these be values that I have observed, I use these values to arrive at an estimate that eventually will converge to the actual value. Right, so this is what Kalman filter is. They call it an optimal estimator of an analog to digital conversion phenomena over here. Right. So over here, the next state is a function of the current state and a certain noise component that comes in because of my measurements. These noise components can be because the instrument that I use to measure these values itself is faulty. Okay, for example, our GPS measurements, our GPS locations, they give you an approximate around which your values can be. They perhaps may not always be able to pinpoint your location. So there is, say, a plus minus 5 points of noise that enters into your measurements all the time. Okay, plus minus a range of 0 to 5 maybe, both inclusive. So Kalman filters, they take 2 steps in order to update their prediction. One is you have a set of observations and you arrive at xt plus 1. So this is a one-step prediction using all these different derivations of all these observations from transition model, same equations that you used in the past for hidden Markov models. It's just the same. You just have an integration over here because the time over here is delta. It's not discrete times at say point at gaps of 1. But over here, the time is far, far smaller. It tends to 0. So you have again a forward generator over here. Here again, you have a transition model over here, the transition values that come in to arrive at just one step prediction, just t plus 1. Okay, and then you utilize this function, this value that you have gained over here, you plug it into this equation to arrive at an updated distribution. So it's using evidences to arrive at xt plus 1, and using this value, this is something that I get from my sensor model. If you remember what we had done in our over here, this is what I get from my sensor value, and this is what I was equating or what I was calculating from my past observations. Same equations over here, same set of equations. It's just that I put this prediction actually into this equation over here. This value comes in over here in order to arrive to correct my distribution. This is essentially what is happening over here. I take one step ahead and I use that value to update my distributions. But in the past, what we were doing is, this is what was happening, same thing. It's just that over here, the time scale has changed. It's just that the time scale has changed. That's all. Okay, this is what is happening for Kalman. And if you remember this sequence, this lecture that I have marked in bold over here in the resources slide, this 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 flow chart that I have drawn over here is from that lecture because I found it very interesting. What they do is the entire process over here is you evaluate a gain value, which is a function of the error in the estimate and the error in the data. This is something like a balancing factor, right? Like if your error in the estimates is somewhat converging or the error in the estimates is on the decline, then we will focus more on the estimated value rather than on the measurements that I am taking. Okay, this is just to balance between estimate versus real observation, this particular fact. If you looked at lecture number 4 and 5, okay, this is what they talk about, this entire flowchart over here. I have a new estimate over here, which is a function of the previous estimate and the data that I have experienced over here. The data I have experienced. The data and previous estimates that I have made, I arrive at a new estimate and I arrive at new error estimates. So I have a balancing factor that tries to balance between new estimates and new errors. Errors meaning the difference between the actual value and what I estimate. Okay, I use this balancing factor in order to kind of allow my equations to converge to the actual. And this again will go back over here. What I estimate, my new error estimate, it will go back into this and this will keep iterating till I converge to actual values. So for example, if I'm trying to find the trajectory of a bird that is flying in the sky and I assume that it's a linear pattern, if I assume that, so then what I do is I look at the bird's position at time t, I make a prediction what is going to happen at time t plus delta, and then I actually see the bird moving to time t plus delta, the new position over there. I find a difference between what I observe and what I have estimated, and then I plug that in into my new estimate again to take another prediction. If you think this is exactly what has been happening in hidden Markov models as well. You were filtering, you were making a prediction, and then you were going back and smoothing it up. This Kalman gain and new error estimate, this is essentially what is happening in terms of the smoothing factor, and this new estimate part over here is the prediction that is happening. It's just that the time scale is different. Here we are updating our distributions are over a certain time span. At instead of discrete times, we are moving at a continuous time observation sequence. But again, I would like to remind you over here, this is in some way an analog to digital conversion. Only over here, the time tends to 0. It's just that. Okay, the time of my prediction, that goes up to infinity. My prediction time goes up to infinity. But the time of my actually taking these observations, that tends to 0. Okay, while for discrete times, it is at regular intervals. Time t equals to 1. That is what I'm doing. But for Kalman filters or for a continuous world, the t tends to 0. That is why I prefer using a delta over there. And if I say that my errors or the noise in my equation is Gaussian, then the Gaussian equations have to be plugged in over here in order to derive at error values. Now that is something that is rather complicated in the book. This is here. They plug in derivations and they plug in the variance over here. into the equation, into this error equation over here. And here we are dealing with more than one variable to define a state. That's why it's multivariate Gaussian. Because if you are trying to look at a bird flying, it's the position coordinates, it's the velocity coordinates, and many, many other coordinates. Okay. So this is for essentially a linear world. But if I do the same for a non-linear world, then I have an extended Kalman filter, and that is far more complex. So for this time, we will just be focusing on linear world. Okay, because giving in too much at this point in time will just confuse things. So I will not move into extended Kalman filters. And tomorrow, Tejas and Arpit will actually be giving you demos of how this is working. Okay, I'm sorry I cannot be there tomorrow, but they will be sharing demos with you in order to actually help you visualize this phenomenon. Fine. So, are there any questions? I am sure there will be a large number of questions because this is something that I too am rather I'm never always very sure about because it's about probabilities and we're only dealing with a certain number of samples. Right, right. That would always that will always be more helpful, I suppose. But what happens over here is if I have an understanding, theory is just to get you acquainted with the terms. Okay. For example, during a demo, if someone says I'm making a prediction or I'm doing a filtering operation, you just know what is happening, what you have and what you are trying to do. Theory just helps you understand it from an umbrella kind of a fashion. And the demo will actually show you how it works. And in the real world, it's all about plugging in all the more features into describing your states. But again, there you have to make trade-offs between the number of features that are essential and the number of features that you might discard. So there are those kind of trade-offs that also you need to think about when you are working in the real world situation. And theory is just to get you acquainted with the terms that are being used to describe a demo. It's just that, nothing else. Right? Are there any? I can only hope that because nowadays what is happening is you have toolboxes available for you. You either have toolboxes in Python, you have toolboxes in MATLAB, which make life easy. But if you are actually going to engineer a system, you will have to design your own toolbox. So now the question that I started my classes with is how do we arrive at these initial predictions? These start predictions. Do I just do random ones and then hope that eventually, if I keep on taking samples, I will converge at the actual at some time tending to infinity? I will perhaps converge at the actual value. That is what we are all trying to do. If you think about direct estimation, what we did in reinforcement learning, we were constantly taking in samples. We were constantly building up this table of frequencies with the hope that this is the model of the real world. Right? So there are many, many such questions that we can all think about that we actually have to work on because over here we are calling it probabilistic reasoning over time, but this is just about states and observations. We are not embedding semantics into this model at this moment. Why is it like this? Because I might be happy, just not depending on the weather, but there are many other factors also. So for a very simplistic model, I just look at the weather. But if I had to make it a little more complicated, then besides the weather, there would be perhaps past conversations or work stress maybe if I have to model the real world. So those kind of factors, they go into your state descriptions over here. If you are now just working with one variable, then you have a hidden Markov model. But if you're working with more variables, so then there are covariances to think about as well, isn't it? How one parameter differentiates with the other parameter. Are the differences long? Are the differences big? Are the differences small over time? So then you have to think about covariances as well, right? So it gets complicated with the more number of parameters that you use to describe your state, but just a single variable is not always a very good thing to do. Fine. So this is what it is. So now it's always good to start with a simple model and then move on to complex models. That is always what we do, and that is what we always try. But yeah, this is how it is. So, any other questions, any thoughts and observations? Because I have asked many questions across what if actually over here again, I will be saying convergence will happen at some time t that tends to infinity. Okay, because you're only taking a few samples of the environment. You're not taking statistics of the entire world. Because that is a combinatorial explosion that would happen if you would have to if you have to consider every state to every state, right? So you are trying to derive an answer from a subset of your entire possible sample space. So the convergence will always happen at some time t tends to infinity. So your iterations have to keep running. If you make your algorithm stop after the fifth iteration, then it will be far from convergence, unless you are very lucky and you have used excellent predictions at the very beginning. So whatever you do, that is fine. Whatever you do, because it all depends on what values you have started with. Right. Any other questions? Any thoughts on those? I'm so sorry I can't talk to you tomorrow. Otherwise, I would be trying to discuss these different big questions that I had put up on the slides earlier, in my earlier slides with reinforcement learning. All these questions on modeling emotions and modeling thoughts and data structures of our thoughts, and how do we model natural language understanding. POS tagging is fine for natural language processing, but if you have to understand, then you have to plug in meaning into your transition probabilities, meaning of one word flowing into the other word. But how do we represent meaning? That is a question again. Right, so there are many such questions that come into play over here, and I don't know if we will get the opportunity to work on this, but yeah, I just hope that I was able to perhaps give you a big picture of things. That's all that I would, that I can only hope about. Yeah. Any questions, any thoughts, or any things that you feel I might have done but I didn't do? Please feel free to share your thoughts. We just have about another 5 minutes before the class ends. Any thoughts, any suggestions, any ideas, anything that you would like to discuss? And if you have any questions, please post them to me offline in the sense of classes, and I shall try my best to get back to you with answers at the earliest. Yeah. Any thoughts? Any suggestions, any ideas? We have about under 2-3 minutes. Yeah. So if there are no questions, and I'll stop sharing my screen. I'll make all of these available to everyone at the end of this class. And I'm so sorry I forgot to share the resources slide in the earlier class. I'm so sorry for having forgotten about that. Any 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 other questions? We just have about 1 minute before we say bye-bye. But it has been absolutely fantastic interacting with everyone in the class. I wish I could actually talk to everyone, but you have been absolutely fantastic in the class, because every class has had a very healthy discussion of questions and problems. And I also see the questions that you keep putting up on the assignments, and Tejas has been very kind to answer all of them. But it shows that that you have been trying to solve it. And if there are no other things to talk about, then yeah. No, it's not about patience. It's just trying to. It's all about exchanges, right? Because I can't say that I am teaching. It's just discussing and trying to make things, represent things in one way, the way I understand it. It's just about that. And I might not be understanding it correctly. It might not be right. Who knows? Right? These are philosophical questions. Maybe we can talk about them later. But yeah, so if there are no further questions, okay, emotion classification project. There is a company called Affectiva that is a spin out from MIT. They do certain work on affect, and then there is Rosalind Picard, who is trying to find a correlation using similar kind of Markov models and Bayesian networks in order to find a connection between affects and states of epilepsy. Rosalind Picard from MIT Media Lab. If you are actually interested in emotion classification and um, its various what shall I say, derivatives in terms of disease and health conditions, mental conditions, then you can look at her work. She is trying to find correlations between that. Heights of emotion with certain sparks leading to an epileptic fit, things like that. And there are many, many questions. In fact, there is a book, if I'm going on seriously with Sanskrit. I think there are initiatives on the same, because Sanskrit is a very, very well structured language. It is very, very well structured. But again, the problem is, how do we encode meanings of words? That is a problem that is always there. Because it's all about natural language in a way. So there are lots of words to think about, and words come with meaning. So how do we represent meaning? And then we have new words coming up, like memes and Googling. These are new words. But still, if someone uses the word, you understand what the meanings are, and you still get along with life. So how do we do that? What kind of models should we use in order to represent meanings of words? That is something that I'm pretty curious about. How do we do it in the brain? These are some questions to think about. Right. So with this, we actually come to the end of the syllabus for Fractal 2. I can just hope that I've been able to share a little bit, share some questions and thoughts and ideas. And tomorrow, Tejas and Narpit will be sharing a few demos on Kalman filters and hidden Markov models. And then we'll have minor 2, I suppose, in a few more days' time. And hopefully we'll meet someday again. So if there's nothing more, then you can feel free to log out and get along with the class that will begin in another 5 minutes, I suppose. Right. Thank you so much. Thank you everyone for being so active in the class. I've received questions from almost everyone and emails as well. It has been fantastic. Thank you so much. Please feel free to log out and get along with your next classes. Thank you, everyone. Have a good day too.